So here are the video model answers for set 1 of the 10 questions that we'll be doing every lesson. So I'm going to go through the questions question by question, one at a time, with some extra detail. So this is set 1 that you will have done as a raw set. There is a printout as well that hopefully your teacher has let you have. If not, please do ask them for the printout to go in your folder. Okay. So the first question, we're looking at standard form here. So in standard form, this means you have to have the answer as just something in the units column, decimal point, and then everything else goes to decimal times 10 to the power of something. Now this power up here is how many places the decimal point has moved. Now in this question, or any question where you've got an ordinary number with lots of zeros on it, then the decimal point is on the end of the whole number. So at the moment, the decimal point, although you can't see it, is here. And you've got to get the decimal point down to here. So you've got just one number, and then everything else is part of the decimal. So 1, 2, 3, 4, 5, 6, 7. Okay, that decimal point would have to move 7 places to get to the correct place. So this answer should be 4.56. All those zeros can disappear now, you don't need those. Times 10. Now we move the decimal point 7 places, and we moved it up the number line. Okay, up the number line 7 places. So it's a positive power of 7. Now, if we were to have a number, let's say like this, if we'd had a number that was 0.000, whoops, 0, just tidy that up a little bit. Let's say 3 to 5. Okay, we need to get our decimal point here in between the 3 and the 2. So let's just change the color. So the decimal point is here. We need to move it 1, 2, 3, 4, 5. That is moving 6 places to get to the right place. So the answer should be 3.25. It's moved 6 places and it's gone down the number line this time. So that makes it -6, a power of -6, because it moved down the number line 6 places. Okay, so this is an ordinary number here, but these are standard form numbers. If you're given this sort of thing, you have to put it back into an ordinary number. What you would do then is you would have your standard form number, just lose the power 10 bit and put a load of zeros on the end here. Okay, and now to get it back to an ordinary number from this standard form, you would move it to the end. 1, 2, 3, 4, 5, 6, 7, because, okay, it says power 7 here. And if I rewrite that, 4, 5, 6, I've got 1, 2, 3, 4, 5 zeros. It does not just mean add 7 zeros. Okay, and you can see that's way back where we started from. Okay, so this is a standard form number, this is an ordinary number, and you could be asked to switch between either ordinary and standard form, or a standard form back into ordinary. Let's do the same with this one. So it's a negative power here, so I'm just going to write this like this, and I'm going to put some zeros on the front here just to help me out. Okay, now the decimal point needs to move 6 places in the opposite direction. If it started out, if it's got a negative power, it means it started out life as a very small number. So it gives you a clue. So it's going to go 1, 2, 3, 4, 5, 6. Okay, it's going to land there. So I've got 1, 2, 3, 4, 5 zeros there. And of course, the leading 0. So 0.1. And then the 3, 2, 5 goes on the end. So that has now gone from a standard form number here, okay, to an ordinary number here. So you can see we're back where we started from. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Always count the zeros. Always do the loops to help yourself out. Okay, so now this one here. You could have this set up as loops. You may have to use your loops for your double bracket expansion. It's a very similar method, or you could use a grid. Okay, so let's do the loop one first. If you loop, you are doing 2x times 3x. That's one part done, the first loop. And you also need to do 2x times positive 5. So this will actually be the same as doing 2 times x times 3 times x. You can split them up because it's all multiplication. So you can tick off the numbers first and you will then get 6, 2 times 3 is 6, and then x times x is x squared. Anything times itself is x, is the thing squared. So down here we have got basically 2 times x. It's good to think about splitting it up. It helps you see that you can do these numbers first. 2 times 5 first is 10, and then you just stick the x on the end because it's all being times by x. So our final answer, 6x squared plus 10x. Okay. If you want to use a grid for that, so I highly recommend the grid if you get confused with the loops, especially when you're doing a double bracket expansion. So in the partition it out, that's positive 5. And then you've got 2x here. So if you can cope with this in one go, it's 2x times 3x. You've got to remember to do the 6. Okay, 2 times 3 is 6. X times x is x squared. 2x times 5, 2 times 5 is 10. Stick the x on because it's all being times by x. And pull that out and you've got the same answer. Okay, 6x squared plus 10x. So either use the loops or use the grid. If it had been a double bracket expansion, you would just have 2 bits here. Your second part would be there and the second bracket. Okay. Okay, so this has got this calculation can be done in several ways. I'm going to show you 3 ways of doing this. And the first way is what you would call the standard algorithm. Okay, and this method has been around for a while, and it might be one that parents or grandparents might push you down to try and use. But if you don't understand it, then we'll do a different method for you later on. So this basically is 30, write that down here, tell you why in a minute, 30 times 56, and it is 4 times 56. Okay, so let's do the 4 times 56 bit first. So 4 sixes. Okay, it's 24. Be very careful when you're carrying here. Okay, we've now got 4 fives is 20 plus the 2 is 22. And that's it for that row. Now, the next bit is where it goes wrong sometimes. So just change my colour. Now, because this next row is actually 30 times 56, but we've moved across to the next column, we need to fill this gap with a 0. It's a placeholder. It's because we're doing 30 times 56. We're not actually doing 3 times 56, although that's what I'm going to say in a moment. So we're now doing, we're doing 3 times 6 is 18. Carry. 3 times 5 is 15, add the 1 is 16. Okay, now we're going to add them up. We've got 4, we've got 10, carry the 1, 6, 7, 8, 9, and the 1. This is where all these carrying bits you did at the beginning have already been used. So it's worth even crossing them off as you add them into this first part of the calculation, as you might count them all up in this final adding. So make sure you cross them off when you've used them. So now we're not adding these carries. These carries here were part of this original calculation when I was doing this bit here. I'm adding up here, and all I've got to carry is this 1 when I made 8 plus 2 is 10. So the second method for doing this one is by using the grid method, which I think a lot of you will have been taught at school. You have to partition again 50 and 34, 50 and 6, sorry, because you've got 56, 56, and you have got 34. So 3 times 5, let's just pretend those zeros aren't there. 3 times 5 is 15. I have drawn my grid rather small here. And then put the 2 zeros back on, because you're actually doing it 10 times 10 bigger. 3 times 6 is 18. Okay, but it's 10 times bigger, so 180. 4 times 5 is 20, but 10 times bigger. Oh, the 0 there. And then 4 times 6 is 24. Now this, you need to bring those numbers out very carefully and line them up so all of the values are in the right column. And then you just add those up. Okay, so we've got 4 there, 8, 9, 10, carry the 1, 5, 6, 7, 8, 9, and the 1 comes down. So the same answer as over here. Okay, so just a different way. Just make sure you have to partition the numbers out and be careful of all your zeros, and then be very careful lining up the numbers as you pull them out here. But this method over here can be confusing with this 0. People forget the 0. I can see now that people probably add those carries into the final line as well as adding them in the first step. So here's the final method I'm going to show you. This is actually called Napier's bones, invented by a Scottish mathematician, John Napier. And it does rely on some setting up to start with. This can be the most tricky bit when you set it up. But it's partitioning it again, but just into the single digit. So that's the difference between this and the grid method. You have these diagonal lines here, and you're setting up the other way around, if you like. So you've got 6 times 3 becomes 18. Okay, 6 times 4 is 24. 5 times 3 is 15. 5 times 4 is 20. Okay, just change my pen color to make it a bit clearer now what happens next. So now you have to use your answers, just the ones that are in the boxes here. So just these ones here in the boxes, in the sections, sorry. So you're not adding these numbers from the side. So this diagonal, it comes to a total of 4. This diagonal, 8, 9, 10, nothing there, comes to a total of 10. I must carry that 1 over here. 5, 6, 7, 8, 9. Don't forget the carry. And then 1 here. So be careful, I'll cross out that carry because I've used it. So the answer is 1904, the same as the other two methods we did. Now, let's say you had, this had been 5.6 times 3.4. This method can be used quite nicely to leave the decimals in and then you slide them down. Some of you may have seen that before. But actually, my top tip would always be, let's make it into 56 times 34. Take the decimal out. And then at the very end of your question, you would then look at putting the decimal back in and counting how many decimal places there are. So let's say if you did this calculation, you would get the answer as you have at the bottom there, 1904. You'd get the same digits, but you then go back to your question. There's 2 decimal places in your question. So there must be 1, 2 decimal places in your answer. So that would give you 19.04. Okay. Now that's about right, because this is roughly 6 times roughly 3, which is approximately 18, and this is close to 18. If that decimal point had been here, that would be 190.4. If it had been here, 1.904, which is totally wrong for this question of this sort of size. That answer is roughly 18, therefore the answer here looks about the right order. Okay, so always think about your decimals. Think about getting a sort of rough estimate first. Even write it down. 6 times 3. Okay, that's 18. So I'm looking at an answer that is roughly 18. That helps you check your decimals if you had to do a decimal calculation as well. Okay, so this one, it's about rounding to 2 significant figures. Now, significant figures get confused with decimal places. So you've got to think about the 2 most significant values. Okay, so you could even think about when you see the word significant figures, cross it out, put significant values, if that's what the question is asking you to do. So the 2 most significant values, if you think about this as being money, this 9 and 8 are the biggest digits, if you like, 9 and an 8. And this 4 is the lowest one, but actually in value, this 4 is worth much more than this £8 on the end here, or this £90 here. So we need to take the highest value. So we're looking at the highest value items, the highest value digits, in accordance with their headings. So we've got units, tens, hundreds, okay, thousands, and tens of thousands there. So we'd rather have this £45,000 rather than £98. But we still need to round. So we're going to look at this number here. The 5 here is going to round up, or is it going to round down on this other 5 here? So it's a 5, so it goes up in general. 5, 6, 7, 8, 9 will round up. 0, 1, 2, 3, 4 would round down and keep this at a 45. So here it rounds up. So we change the 5 to a 6. We have to put the 3 zeros on the end. Otherwise, we would just have £46. We want £46,000. Okay, so significant values just means the highest value heading. Now, if you'd had something like this, however, okay, 8, 7, 4, and they wanted that to 2 sig figs, called significant figures, then these 2 zeros don't count. They're just holding the place. There's nothing of any value above this 2. So the highest value is this 2. Okay, it's worth hundredths. If that's in money, it'd be pennies. Okay, so we've got hundredths here. This column is thousandths. So that's the next most valuable, and so on, and as you go down the line. So 2 sig figs. So these 2 zeros don't count for anything. If there'd been a number up here, like a 7 or something, you would start counting there, and it would then be the 7 and the 0. This 0 here would be the most significant. But here, nothing in front, so we count here. So 1, 2 places we have to look at the third to round. That 7 is going to tell us to round up. So it becomes 0.029, okay, to 2 sig figs, which is short for significant figures. It might be SF. Okay, but what if they had asked you to round that second one to decimal places? So let's just show you what would happen if it had been a decimal place, this one. So if it's 2 decimal places, 0.02874. So decimal places, you start counting from the first decimal place, and that's the second decimal place. So therefore, we're looking at the 8 now. And to 2 decimal places, that means only 2 digits are allowed after the decimal point. That 8 is going to round that 2 up. So this one would be 0.03, and that's to 2 decimal places. So really quite different to this one over here. Sig figs, you start counting at the one that's got some value. Decimal places, you start counting straight after that decimal point. Okay, so this question is all based around the equation that hopefully you know, or you're going to try and remember, y equals mx plus c. Okay, sometimes you see this equation when you get it given a line, you get it written in this sort of form. You get the constant given first, and then you might see plus or minus the mx bit. Okay, so the x bit could come at the end. So just watch out for this. It's just been flipped around from this. But what it means is, whichever way round it is, the bit that is stuck next to the x is the gradient. Okay, that's how steep it is. And the bit that's stuck on the end, that is the constant, that is the y-intercept. That is where it crosses the y-axis. So this is still the gradient here. Whatever is stuck onto the x is the gradient. Oops, gradient. Okay, and this will be the y-intercept here. Now, it does matter what the sign is in front of that m. Okay, in front of the m bit, then you have to take the sign with it. So I'll show what I mean in a second on that. But for this one, we've got the y equals 6x minus 2. So we're looking at this bit here, where after the gradient, we just literally take that 6 off there. So the gradient, so I'm struggling there, gradient, okay, is 6. Not 6x is not equal to 6x, okay, that would be wrong. Just the 6, you just take the value off. Now, if you had example over here, y equals, let's say 3 minus x, okay, well, the gradient is not 3. The gradient is the bit that's stuck on the x. Now here, what is the number stuck on the x here? When you don't see a number in front of the x, there is an invisible 1 there. So in that case, our gradient is going to be minus 1. You take the sign with it, the negative number, the negative sign here, and there is actually a 1 there. We don't tend to write it, but there is an invisible 1, therefore the gradient is minus 1. The other one to be aware of is if you had this sort of thing. If you had 2y equals 4x, okay, minus 2. Now this is where we have to have it as y, just one y. We cannot just lift the gradient off otherwise. So to get just one y, we have to divide the whole row by 2, and we have to do that on both sides. So if you haven't got one y, you have to divide it through. If you haven't got it in this right format, you've got to think, well, where is my bit stuck on my x? So it's just a bit of adjustment. So divide by 2, I get 1y. Divide by 2, I get 2x. Divide by 2, I get minus 1. So for this one, the gradient is equal to positive 2 because it's just positive 2 there. Okay. Okay, now this one, you've got kilometers here, and they're talking about nearest 100 meters here. So this should always make you think, I've got 2 different units of measure. So you need to actually make them so they're the same unit of measure. Because 1 kilometer equals 1,000 meters, to get from kilometers into meters, you would times by 1,000. So 5.342, there's your first bit, kilometers. Okay, I'm going to times it by 1,000. Now, that isn't adding 3 zeros, it's moving the decimal point 1, 2, 3 places. That's going to equal 5,342 meters. Now, often there is a mark just for doing that conversion. Okay, not for quoting the conversion like this, but actually using the conversion. So often you get 1 mark in a question that needs you to do some sort of conversion. So now we look at 100 meters. Now this is units of meters, tens of meters, hundreds of meters, thousands of meters. Okay, so we need to stop at this point. So we need to look at that 4. Now that 4 is on the lower end of our rounding scale. So if we're going to round it, so this is an approximation symbol, we're going to have 5300 meters. That has been rounded to the nearest 100 meters. Now, because they started out in kilometers, they haven't asked you to put it into kilometers, but it makes sense to go back to what they started. Put it back into kilometers, you need to divide by 1,000. So undo that conversion you did at the start to get to kilometers. So decimal point is here. It will move 1, 2, 3 places because you're dividing by 1,000. You end up with 5.3 kilometers. Okay. So the next question. Right. This question can be done in several different ways again. But because it's a non-calculator question, there are 2 methods that are a bit easier than the standard method you would use for calculator. For percentage change, okay, what is the percentage change? What was the increase? What was the decrease? Okay, what was the sale offer? Any of these sorts of questions. What was the reduction? So it's always going to be the difference. So the difference between your first price and the second price you were given. And you have to divide it, okay, by the original price. So this is a standard formula. And at the end, you would times it by 100 because this bit here would give you a decimal, and then you can lift out the percentage. Some of you might spot it, but times it by 100 gives you the actual percentage. So this is your first price, okay, and this is your second price, okay. So the difference between those 2. Now, if we had a calculator, we would be doing the difference, which is 65, okay, divided by the original, which is 500, and then times by 100. But to do this, okay, to do 65 divided by 500, that is this sort of calculation, okay, if you were to do this, and it's really quite tricky, okay. So without a calculator, we could fiddle around with this and explain why it works, but you know what? There's a much easier way of doing this one. If you're trying to get that into a percentage, all you need to do is think about, right, if I can get this fraction here into hundredths rather than 500ths, all I then need to do is lift off this top number here, and that is my percentage. So I'll just change my pen color. See if you can be thinking what that answer might be. So to get from 500 to the magic 100% out of 100, all percent means is out of 100 parts. So I just divide by 5. Okay. Therefore, I have to do, these links are always repeated. You do the same to the top as you did to the bottom. I must also divide by 5. So now I can do a nice simple bus stop here. Okay, so I'm doing 65, divide by 5 if you need to do this. You might want to use the fact that 10 5s are 50, but 5s and 6 goes 1, carry the 1, there's 1 left over. 5s to 15 goes 13, so that's 13 hundredths. 13 hundredths equals 13%. Okay, and a quick check. If you thought, well, what's 10% of 500? Okay, 10% equals 50. 1% equals 5. Oh, look, so if I'd had 3%, 3% would equal 15. So 50 plus the 15, there's your 65. 10% plus the 3, there's your 13%. Now, another way of doing this, which was demonstrated by a student, very sensible way of doing this, is to look again at the difference. So the difference is £65. Okay, that's your difference. Now, there's no dividing going on here, okay, at all for this method. Just change my pen colour. You're going to be thinking, well, hang on, well, let's go look at the original then. What is 10% of that original? So it's based on sort of a bit of trial and improvement here. So 10% of the original £500 equals £50. So it's not a big enough difference yet. We're looking for £65. So 1%, this links back to my check method in the last example of £500, is £5 because I've just divided that 10% by 10 or this by 100. So therefore, hang on, we've got £55 now. If I had 50, 5, 10, 50, and I had 3 lots of that, okay, then I'd have my £65. There's a little bit slow method, but there's no dividing involved really apart from dividing by 10 or dividing by 100. So 3% is going to be £15. And just like the check method, I've got 50 plus 15 is my £65 difference. Therefore, the percentage increase must be 13%. It works. Okay, so you decide which method you think is best for you, but just don't forget percentage change is the difference between the first and the second price, always divided by the original. Right, with this one, we could use our line up and link method for this. We've got our pens and our costs. Now this line up and link is brilliant in lots of ways, helps you just really structure your question. 12 pens is £2.40, and they want you to find out in the end what 9 pens equals. Okay, so the best way of doing this, a nice way of doing this, is to think, right, what's the cost of 1 pen? So to find the cost of 1 pen, to get from 12 to 1, I just divide by 12. From a number, any number, to 1, just divide by the number you start with. But you've got to do the same on both sides. So divide by 12. Okay, so hopefully you can spot 12 and 24 as a link, but if not, 12's into... Now you could do it like this, 2.4. You can make it 240 and change it back at the end. But look, don't be scared of dividing like this. Decimal point just jumps up on there. 12's into 2 doesn't go. I've got 2 left over. I've not used those 2. 12 into 24 goes twice. 12's into 0, it doesn't go. So 20, 0.20. Okay, so 0.20, or that's in pounds, or that's 20p each. Now always make sure you write down that you've converted it into 20 pence, as you could end up getting confused and then getting a really silly big number for the end because you didn't put it back into pounds. So now we've got to go from 1 to 9. So we're going to times that by 9. We need to get from here to our final answer. So the same link times by 9. Here, we're just doing 9 times 20p, or 9 times 0.2. So 9 times 2 is 18. Put that 0 back and then 10 times bigger, 180p. Make sure you put the pence on, because now you're thinking, right, I can either write the answer as 180 pence, or back in the unit of measure they gave you in the first place, and that should be divided by 100, so you get your final answer in pounds of £1.80. No pence on the end of this one because it's got a pound sign at the front. So always looking for the cost of one item is a good, safe way of doing it. There are other ways of doing this, but if you go back to one each time, it's a pretty secure method. Okay, so this one does tend to worry people quite a lot because you've got x's on both sides and an equal sign in the middle. What's that about? Now, this solve does mean they want you to find an actual value for x at the end. You just solve it and get an actual number for x at the end. X on its own, just one x. So first you need to think about is getting all the x's on one side and all the sort of constants on the other side, the single numbers on the other side. So my recommendation is always to move the smaller amount of x or y or z or whatever it is, move the smallest amount. because then you won't end up with negative x's. So let's just change the pen so this makes it a bit clearer to see. Okay, so I'm going to move this 4x. Now you could use this sort of stacking up method where you put minus 4x there, and the same must be done to both sides. So I'm taking away, I'm doing 4x, take away 4x. That leaves you with no x at all. Okay, I wouldn't write no x. You can if you think you need to, but in the exam you'd need to leave it with not the no x there, the 0x. So 4x minus 4x, you've got rid of it. All you're left with is minus 9. So that has basically gone. Here 6x minus 4x is 2x. I've still got this positive 5. Don't try and do it all in one go. You are likely to get into a bit of a muddle. Okay, so let's change the pen again. So now we're going to move this 5. Now this 5 is positive, so I'm going to take away the 5 there. Okay, take away the 5 from this side, and I also need to take away the 5 from this side. So this will disappear, we'll cancel it out. Change the pen to make it a bit clearer for you. Okay, so this goes, okay, positive 5, take away 5 gives you 0. And this side, minus 9, if you're not sure, write it out, minus 9, take away 5. Ever you get negatives, just write it out to the side because it can get it much clearer in your head. I'm at minus 9, I'm taking away 5 more, I'm going to land on minus 14. And a little clue here is you've got quite a nice number there. Okay, if you get a dodgy number, you can almost be sure you've gone wrong in a non-calculator question. So here we've now got one step left to do, and that is to just divide by 2 to get the single x. So divide both sides by 2. I'm left now, sorry, change colour again. So I'm now left with 2 on this, with x on this side, and with minus 7 on this side. Okay, so x is equal to minus 7. Okay, so this question, we have got, oops, go back, sorry. I'm struggling with the pen here now. Right, back on track. Okay, so this question, we have got given a side, and we've been given another side, and we're trying to find the third side. So with anything with a right angle triangle, okay, and you've got a side and a side, you're trying to find another side, we are dealing with good old Pythagoras' theorem, which I'm pretty sure most of you have come across before. So just need to recall what the theorem is, and the theorem is a squared plus b squared equals c squared. That means if you had a square drawn off this side and a square drawn off this side, those two squares would add to make the bigger square here. Okay. Likewise, you could be asked to give one of the shorter sides, find one of the shorter sides, and that shorter side would be the big side. Take away this side, gives you the shorter side, the square of the shorter side. So it's all about squaring. Okay, just change my colour pen. So we need to be able to do square numbers here, okay, without a calculator, which should be quite straightforward. So definitely need to know your square numbers up to at least 12 times 12. I recommend you know up to 15 times 15 if you can. And you need to know your cube numbers as well. They'll expect you to know those off by heart without a calculator. Just up to about 5 or 6 cubed. If you can do those, it'll be even better. So we can call either of these short sides A and B, but the longest side has always got to be C. So C is always the longest. Proper name for that is the hypotenuse. Okay, which you may have come across if you've done any sort of trigonometry at all, but the technical name is hypotenuse, but this is Pythagoras. So we're going to take the A value, 6, and square it. We're going to add it to the b value of 8 and square it, and we're going to try and get a value, the c squared. 6 squared is 36. Okay, 8 squared, 8 times 8 is 64. And I'm going to keep this c squared here. So we're always thinking, what are we trying to find? Rather than write the total here, I'm going to write the total here. So if you're not sure, never just guess it. Always put it at the side. If you need to just a quick adding up, rather than get it wrong in your head, that's 10, 6, 7, 8, 9, 10. Okay, so it's 100. So just to be sure, you're not, in exam pressure, write it out at the side. So c squared is 100. Now, if you were to write that the answer was 100 now, it'd be a bit ridiculous. You've got a side that's 8 and a side that's 6, so this can't possibly be the length 100. It's far too big to fit in between these two lengths here. So it doesn't look right. It's a bit of a silly answer. So you've got to think, what else do you need to do? And the answer to that is you need to square root both sides. So if you square root this side, okay, then let's write it on here. If you square root c squared, okay, and you square root 100, okay, what's happening there is this square and this square root cancel out because they're inverses. So now you're left, let's actually do the calculation here, we're left with what times what, okay? Something squared equals 100, which means something times itself equals 100. And hopefully you all know that 10 times 10 is 100, so 10 equals C. Okay, so that's quite straightforward. It's actually based on a 3-4-5 ratio triangle, so you've got nice numbers going in, nice numbers coming out to get a nice round square root, sorry. But here's an example, still non-calculator. You don't have to have the calculator to finish this off. So you've still got Pythagoras, you've still got a squared plus b squared equals c squared. Okay, so let's add that in. Let's have 5 squared plus 7 squared equals c squared. So we've got 25, 5 times 5 plus 7 times 7 is 49. Okay, as I say, don't try and just do that in your head. Write it to one side, especially in the exam pressure. 9 plus 5 is 14. 4, 5, 6, 7. Okay, 74 is c squared. So if you keep this c squared going down here, you're not going to hopefully say, oh, this line here is worth 74. No, c squared is 74. So again, you think about square root, you need to square root both of them. Square root of c squared, square root of 74. Now, this cancels out. The square root and the square sign cancel each other because they're inverses. So we're left with c being the square root of 74. Now, that is where, with a non-calculator paper, you can leave it. Okay, that is an absolute accurate answer. Okay, if you did it on a calculator, you'd have whatever recurring decimal, a decimal that goes on, and it wouldn't be as accurate. This root 74 is the most accurate measurement you can get. It's a bit like pi. The value pi is accurate. 3.14 blah 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 is not accurate as a symbol pi. Same for this. So if they wanted you to estimate, given that, estimate what it is, then actually you can do that, because what's the nearest square number either side? Now, 8 times 8, okay, is 64, and 9 times 9 is 81. So it's going to be between these two numbers. So an estimate, okay, an approximation would be C is approximately, let's say 8.5, somewhere in between those two, but this is much better. This is just a rough approximation. So you can see, you can leave it as this root sign answer. Okay, so that's an alternative question 10, but still without a calculator. So there are the answers in one go. You need to look at those. And then finally, this is the set of questions you should get a printout from your teacher to keep in your folder so you can follow this through. But of course, now you have the video to also pause, rewind. There's lots of extras in this video than are on this sheet. There's just not enough room on the sheet to put them all on there. Okay, good luck.